45 seconds. That's how long it took for a perfectly functioning Bombardier Challenger 650 to go from cleared for takeoff to upside down on the runway. 45 seconds during which the laws of physics, the principles of aerodynamics, and the deadly sensitivity of swept-wing aircraft to ice contamination all converged to flip a $30 million business jet on its back and kill 6 people. Today, we need to talk about what happens to an aircraft wing when ice contaminates its surface. Not in general terms, not in abstract concepts, but in specific technical detail. Because understanding why the Challenger crashed in Bangor, Maine on January 25, 2026, requires understanding something that most people never think about: the incredibly delicate balance of airflow over a wing, and how even a microscopic layer of contamination can destroy that balance in a fraction of a second. We're going to talk about swept wing aerodynamics, about critical angle of attack, about asymmetric stall, and about why the Bombardier Challenger 600 series has killed people in this exact scenario multiple times, despite decades of warnings, regulatory action, and industry awareness. This is a technical deep dive into how wing contamination flipped a plane on its back, and by the time we're done, you're going to understand exactly why ice on a wing isn't just a performance problem. It's a death sentence. Let's start with the basics of how a wing works, because you can't understand what goes wrong until you understand what's supposed to happen when everything goes right. An aircraft wing generates lift through a process called Bernoulli's principle combined with Newton's third law. Air flows over the top and bottom surfaces of the wing. The wing is shaped, this shape is called an airfoil, so that air traveling over the top surface has to travel a longer distance than air traveling over the bottom surface. That means the air on top is moving faster. Faster moving air creates lower pressure. Slower moving air on the bottom creates higher pressure. That pressure differential, high pressure pushing up from below and low pressure pulling up from above, creates lift. The amount of lift generated depends on several factors: the shape of the airfoil, the speed of the aircraft, the density of the air, and critically, the angle of attack. Angle of attack is the angle between the wing and the oncoming air. When you're flying level and fast, your angle of attack is low. When you're climbing or when you're slow, your angle of attack is higher. As you increase angle of attack, you generate more lift, up to a point. But there's a limit. If you increase the angle of attack too much, the smooth airflow over the top of the wing breaks down. It becomes turbulent. It separates from the wing surface. And when that happens, lift disappears. That's called a stall. Not an engine stall, an aerodynamic stall. The wing stops generating lift and the aircraft starts falling. Now let's add complexity. The Bombardier Challenger 600 series doesn't have straight wings. It has swept wings. The wings angle backward from the fuselage instead of sticking straight out. Swept wings have advantages. They reduce drag at high speeds. They improve fuel efficiency. They allow the aircraft to fly faster. But they also have disadvantages. Swept wings are more prone to a phenomenon called tip stall. Here's why. On a straight wing, when you approach the stall angle of attack, the entire wing stalls at roughly the same time. The airflow separation starts at the root of the wing near the fuselage and progresses outward. That gives you warning. You feel buffeting. The controls get mushy. You have time to react. But on a swept wing, the airflow dynamics are different. Because the wing is angled backward, the airflow has a span-wise component. Air doesn't just flow straight over the wing from front to back. It also flows from root to tip along the span of the wing. That span-wise flow tends to accumulate at the wingtips, and when you approach stall angle of attack, the tips stall first. The outboard sections of the wing lose lift before the inboard sections do. That creates a very dangerous situation, because if one wingtip stalls before the other, You get asymmetric lift. One wing is still generating lift, the other isn't. The result is a sudden, uncommanded roll. The stalled wing drops, the other wing rises. And if you're at low altitude and low airspeed, you don't have time or energy to recover. The Bombardier Challenger's swept wing design makes it particularly susceptible to tip stall. Aviation engineers know this. It's been documented, it's been studied, and aircraft designers use several techniques to mitigate the problem. They use vortex generators, small fins on the wing surface that energize the boundary layer and delay flow separation. They use wing fences, barriers that prevent span-wise flow from accumulating at the tips. They carefully design the wing twist, called washout, so that the root reaches critical angle of attack before the tips do. All of these techniques help, but they all rely on one critical assumption, that the wing surface is clean, that the airfoil shape is exactly what the designers intended. Because if you change the shape of that airfoil, even by a tiny amount, all of those carefully engineered protections can fail. And that's exactly what ice contamination does. It changes the shape of the wing. Let's talk about what ice does to an airfoil. When ice forms on a wing, it doesn't form a smooth, uniform layer. It forms irregular shapes, ridges, bumps, rough surfaces. Even the thin layer of ice, something that might look insignificant to the naked eye, creates massive disruption to the airflow. That smooth laminar flow that's supposed to travel over the wing gets disturbed. It becomes turbulent much earlier than it should. The boundary layer, that thin layer of air right at the wing's surface, separates prematurely. And when the boundary layer separates, lift drops dramatically. Ice contamination can reduce the maximum lift coefficient of a wing by 20 to 30%. It can reduce the stall angle of attack by several degrees. What that means in practical terms is that a wing that would normally stall at 15 degrees angle of attack might stall at 12 degrees with ice contamination. And a wing that would normally generate 10,000 pounds of lift might only generate 7,000 pounds. Those numbers matter. They matter enormously, because at rotation speed during takeoff, you're operating near the critical angle of attack. You're asking the wing to generate maximum lift at relatively low airspeed. And if your wing stalls prematurely because of contamination, you're going into the ground. Now let's make this even worse. Ice contamination is almost never symmetric. Even if you fly through the same icing conditions, even if both wings are exposed to the same precipitation, ice doesn't accumulate identically on both wings. Maybe one wing has slightly different surface temperature. Maybe the airflow is slightly different. Maybe the de-icing fluid coverage was slightly uneven. Whatever the reason, one wing ends up with more contamination than the other. And that asymmetry is what kills people. Because when you rotate for takeoff, when you pull back on the yoke and raise the nose to lift off the runway, both wings are asked to generate lift at a high angle of attack. The clean wing, or the wing with less contamination, responds normally. It generates lift. It's doing its job. But the contaminated wing reaches its stall angle of attack first. The airflow over that wing separates. Lift drops. And suddenly you have one wing generating lift and the other not generating lift. The result is instantaneous. The contaminated wing drops. The aircraft rolls toward that wing. You're at low altitude, maybe 50 feet off the ground. You're at low airspeed, maybe 140 knots. You're at high angle of attack because you just rotated. And you have no time and no energy to recover. The roll rate accelerates. Within seconds, you're inverted. You crash back onto the runway upside down. That's not a theoretical scenario. That's exactly what has happened multiple times to Bombardier Challenger aircraft. And that's exactly what happened in Bangor on January 25th. Let me take you through the historical precedents, because this has happened before and the lessons should have been learned. November 28th, 2004, Montrose Regional Airport, Colorado. A Bombardier Challenger 600 is preparing to depart in light snow and mist. Temperature is -1 degree Celsius. Visibility is 1.4 miles. The crew conducts a visual inspection of the wings. They see what they describe as trace amounts of frost or ice, nothing that looks significant. They don't feel it warrants a de-icing treatment. They're cleared for takeoff on runway 17. They begin their takeoff roll. They accelerate normally. They reach rotation speed, and the pilot pulls back on the yoke. The nose comes up. The aircraft begins to lift off the runway, and then, suddenly, the left wing drops. The aircraft rolls to the left. The left wingtip strikes the runway. The aircraft continues to roll. It goes inverted. It impacts the ground. 3 people are killed. NBC Sports chairman Dick Ebersol is seriously injured. His son, Teddy Ebersol, age 14, is killed. The pilot and flight attendant are killed. The NTSB investigation determined that there was ice contamination on the wings. Not a thick layer, not something obvious, trace contamination. Ice crystals that had formed on the wing's surface. Some of it was so thin it was nearly imperceptible, but it was enough. When the aircraft rotated, when the angle of attack increased, that trace contamination disrupted the airflow over the left wing. The left wing stalled. Asymmetric lift caused the roll. The aircraft flipped. The NTSB determined that the probable cause was the pilot's decision to take off with ice contamination on the wings. But they also determined that Bombardier had not adequately disclosed in their flight manuals and training materials just how sensitive the Challenger wing was to contamination. The manual said ice contamination could affect performance, but it didn't say that trace amounts invisible to casual inspection could cause loss of control. It didn't say that the Challenger's swept wing design made it prone to asymmetric stall. It didn't say that taking off with any contamination, even amounts that seemed insignificant, could kill you. 2 years before Montrose, January 2002, a Challenger crashed in Birmingham, England, during takeoff in winter weather. Similar circumstances: wing contamination, asymmetric stall at rotation, aircraft rolled inverted, multiple fatalities. British investigators reached similar conclusions. The Challenger's wing design was extremely sensitive to contamination. Even small amounts could cause catastrophic loss of control. After both of these accidents, regulatory agencies took action. The FAA issued new rules clarifying that any frost, ice, snow, or slush on critical surfaces must be removed before flight. No exceptions. No judgment calls about whether it's significant enough to matter. All contamination must be removed. They updated the de-icing standards. They required more thorough inspections. And in 2008, they issued Airworthiness Directive 2008-11-51 specifically for the Bombardier Challenger 600 series. That directive required Bombardier to revise the flight manual to include explicit warnings. The warning states, in bold text, that ice, frost, or slush on wing surfaces can result in loss of control of the aircraft during takeoff. It states that even small amounts of contamination can significantly affect the aircraft's handling characteristics. It states that pilots must ensure all contamination is removed before flight. That directive was issued 18 years ago. Everyone operating a Challenger should know about it. It's in the flight manual. It's in training programs. It's been the subject of safety bulletins and industry publications. And yet, here we are in 2026, and another Challenger has crashed in identical circumstances. Wing contamination. Takeoff in winter weather. Asymmetric stall at rotation. Aircraft flipped inverted. All occupants killed. So what happened in Bangor? Let's reconstruct the sequence based on what we know. The Challenger arrived from Houston at approximately 6:09 p.m. The aircraft sat on the ground for over an hour and a half. During that time, the temperature was below 3 degrees Fahrenheit. That's minus 16 Celsius. The aircraft's metal surfaces were cold-soaked. Any moisture that contacted those surfaces would freeze instantly. Snow was falling. Ice pellets were falling. The aircraft was being exposed to continuous contamination. At some point, the crew taxied to the de-icing pad. They received a de-icing treatment. Type 1 fluid to remove existing contamination. Type 4 fluid to protect against new accumulation. The Type 4 fluid is a gel that spreads across the wing surface and prevents ice and snow from adhering during the taxi and takeoff. It's designed to last for a certain amount of time called holdover time. In heavy snow, at very cold temperatures, that might be 20 minutes. The Challenger spent approximately 20 minutes at the de-icing pad. Then they taxied to runway 33. That taxi probably took several more minutes. So by the time they're ready to take off, they're at or beyond the holdover time for the de-icing fluid. They're also taxiing through active precipitation. Snow is falling, ice pellets are falling, and as another crew, the Allegiant crew, had discovered just minutes earlier, that precipitation was overwhelming de-icing protection. The Allegiant crew described it perfectly. It stuck to us like there was nothing there. The de-icing fluid wasn't providing protection. The precipitation was penetrating through the fluid and bonding to the wing surface. The Allegiant crew failed their contamination check and refused to take off. But the Challenger crew didn't know that. They were cleared for takeoff, they advanced the throttles, the Pratt & Whitney Canada engines spooled up to full power, the aircraft began to accelerate. 80 knots, 100 knots, 120 knots. They're committed now. They've passed the point where they can safely abort. They continue accelerating. 140 knots, 160 knots. VR, rotation speed. The pilot pulls back on the yoke. The nose comes up. The angle of attack increases. And somewhere during that rotation, probably within 2 or 3 seconds, the left wing reaches its contaminated stall angle of attack. The airflow over the left wing separates. Lift on that wing drops precipitously. But the right wing is still generating lift. Maybe the right wing has slightly less contamination. Maybe the airflow over the right wing hasn't separated yet. Doesn't matter. What matters is that you now have asymmetric lift. The left wing is generating maybe 7,000 pounds of lift. The right wing is generating 10,000 pounds. That 3,000-pound differential creates a rolling moment. The aircraft begins to roll left. The pilot feels it immediately. The yoke is being pulled to the right by the rolling motion. Instinctively, he applies right aileron, trying to stop the roll. But the ailerons are on the outer sections of the wing, the sections that are stalled. They're not effective. The roll continues. It's accelerating now because as the aircraft banks, the lift vector tilts. You lose vertical lift component. The aircraft starts to descend even as it's rolling. Within 3 seconds, the aircraft has rolled 60 degrees. Within 5 seconds, it's past 90 degrees. It's inverted. The nose drops. The aircraft is now diving toward the runway upside down. The pilot is pulling back on the yoke, but pulling back when you're inverted makes you dive faster. The aircraft impacts the runway on its back. The fuselage crushes. The fuel tanks rupture. Fire erupts. Everyone on board dies instantly. That entire sequence, from rotation to impact, probably took less than 10 seconds. 10 seconds during which the pilots had essentially no chance to recover. Because once you have an asymmetric stall at low altitude and low airspeed, the physics are unforgiving. You need altitude to recover from a stall. You need to lower the nose, reduce angle of attack, allow the airflow to reattach, and rebuild airspeed. But if you're 50 feet off the ground, you don't have altitude to give up. You need airspeed to generate control authority. But if you're at rotation speed, barely above stall speed, you don't have excess airspeed to work with. You need symmetric lift to control the roll. But if one wing is stalled and the other isn't, you have no way to generate symmetric lift. You're a passenger. The aircraft is doing what physics dictates. And physics dictates you're going to crash. Let's talk about why swept wings make this worse. On a straight-wing aircraft, when you approach stall, you get warning signs. The aircraft buffets, the controls get mushy. The stall often starts at the wing root, near the fuselage, where the pilot can feel it through control feedback. You have time to recognize what's happening and take corrective action. Lower the nose, reduce angle of attack, add power. But on a swept-wing aircraft, especially one with contamination, the stall can be sudden and occur at the wingtips first. There's less warning. The roll happens faster. And because the roll is initiated by the outboard sections of the wing, the sections furthest from the center of gravity, the roll rate is higher. You go from wings level to 60 degrees of bank in 2 seconds. Try to recover from that at 100 feet altitude. You can't. It's not possible. The numbers don't work. By the time you recognize what's happening, process it, decide on a corrective action, and begin to implement it, you're out of altitude. There's another aerodynamic factor at play here that makes swept wings stall even more dangerous. It's called adverse yaw. When you apply aileron to try to stop a roll, the down aileron on the rising wing creates more drag than the up aileron on the dropping wing. That drag differential creates a yawing moment that actually makes the roll worse. It's called adverse yaw because it's adverse to what you're trying to do. On a normal flight at normal speed with good control authority, adverse yaw is manageable. You coordinate with rudder. But at low speed, at high angle of attack, with one wing stalled, adverse yaw becomes a significant factor that amplifies the roll. The more you try to stop the roll with aileron, the worse the roll gets. It's a trap. And pilots who aren't trained for it, who haven't experienced it in a simulator, often make it worse by applying more and more aileron trying to level the wings. The correct recovery from an asymmetric stall is counterintuitive. You need to reduce angle of attack immediately, push forward on the yoke, lower the nose, even though that makes you descend. Even though every instinct is screaming at you to pull back and climb, you have to reduce angle of attack to allow the stalled wing to unstall. Once both wings are generating lift again, once the airflow has reattached, then you can start to recover. But that requires altitude. At least 500 feet, probably more. If you're at 50 feet when the stall happens, you don't have 500 feet to give up. You have 5 seconds before impact. And in those 5 seconds, there's no recovery possible. The Montrose Challenger pilot tried. The NTSB found evidence that he applied full opposite aileron and full power. Didn't matter. He was out of altitude before the aerodynamics could respond. The Birmingham Challenger pilot tried. Same result. And the Bangor Challenger pilot tried. 45 seconds from takeoff clearance to impact. Less than 10 seconds from rotation to impact. No time to recover, no altitude to work with, no options available. Here's what makes this so frustrating from a safety perspective. This accident type is completely preventable, 100% preventable. Don't take off with contaminated wings. That's it. That's the whole solution. If your wings are clean, if there's no ice, no frost, no snow, no slush, if the airfoil shape is exactly as designed, the Challenger flies beautifully. It's a good aircraft. It's safe. It has excellent performance. But if you take off with contamination, you're risking an asymmetric stall that can kill you. And the Challenger's swept wing design makes it less forgiving of contamination than other aircraft types. A straight-wing aircraft might be able to take off with trace contamination and experience reduced performance but maintain control. The Challenger can't. The Challenger's wing will stall asymmetrically and flip the aircraft. That's been proven by 3 fatal accidents and numerous incidents. So why does it keep happening? Why, despite decades of warnings, despite regulatory action, despite NTSB reports and safety bulletins and flight manual revisions, do pilots keep taking off with contaminated wings? Part of the answer is subtle contamination. Ice contamination can be difficult to see, especially trace amounts. In certain lighting conditions, on certain surfaces, A thin layer of frost or ice can be nearly invisible. Pilots conduct visual inspections and don't see anything that looks significant. They make a judgment call that it's acceptable, and they're wrong. Because what looks insignificant can be aerodynamically catastrophic. Part of the answer is time pressure. In private aviation, there's often pressure to complete the mission. Passengers are waiting, schedules are tight, delays are expensive. And going back for another de-icing treatment means more delay, more cost, more inconvenience. So pilots convince themselves that they're fine. The de-icing was recent. The holdover time hasn't been exceeded. Other aircraft are taking off. It's probably okay. And they roll the dice. Part of the answer is lack of recent experience with contaminated wing stalls. Most pilots will never experience a stall in actual flight, let alone an asymmetric stall. Stalls are practiced in training, in simulators, at altitude where recovery is possible. But the visceral experience of having a wing drop at 50 feet during rotation, that's not something most pilots have experienced. So the danger remains theoretical. They know intellectually that it's dangerous, but they haven't felt it. They haven't experienced that sickening roll, that horrifying realization that the controls aren't responding, that instant of recognition that they're going to crash. Because if you experience that at 50 feet, you don't get a chance to learn from it. You're dead. And part of the answer is systemic. The de-icing system, the holdover timetables, the pre-contamination checks, all of it assumes that pilots can accurately assess whether their wings are clean. But that assumption breaks down when contamination is subtle, when weather conditions are changing, when precipitation is mixed, when ice pellets are falling instead of snow. The NTSB is going to investigate this Bangor crash thoroughly. They're going to examine the wing wreckage looking for evidence of ice contamination. That's going to be challenging because of the post-impact fire. But there may be witness testimony, photos, or other evidence. They're going to calculate whether the holdover time was exceeded. They're going to interview the de-icing crew to determine what type of fluid was applied and how much. They're going to examine the weather data to determine exactly what was falling from the sky. They're going to analyze the flight profile to determine the rotation speed, angle of attack, and roll rate. They're going to compare this accident to Montrose and Birmingham to see if there are common factors. And they're going to issue findings and recommendations aimed at preventing it from happening again. But here's the hard truth. The solution already exists. Don't take off with contaminated wings. Check your wings thoroughly. If there's any doubt, any question, any uncertainty, go back for another de-icing treatment. Delay the flight. Wait for better weather. The solution is simple, but implementing it requires overcoming human factors, overcoming time pressure, overcoming subtle biases, overcoming the tendency to convince yourself that it's probably fine. And until we solve those human factors problems, until we find a way to ensure that pilots never take off with contaminated wings, this accident is going to keep happening. The Challenger's swept wing design will continue to punish contamination with sudden, catastrophic, unrecoverable, asymmetric stalls. And people will continue to die. 6 people died in Bangor because ice contaminated their wings. That ice disrupted the airflow. That disrupted airflow caused one wing to stall during rotation. That asymmetric stall caused a roll. That roll at low altitude with no recovery options caused a crash. 45 seconds from cleared for takeoff to impact. 10 seconds from rotation to death. That's how fast the aerodynamics of swept wing contamination can kill you. That's the physics. That's the reality. That's why wing contamination flipped this plane on its back.